Okay, hello, thank you for coming. Today we're going to talk about the birth-death process and the non-exponential distributed processes. Okay, so let's start with the birth-death processes. This kind of stochastic systems correspond to a set of discrete possible states that comes from 0 to infinite. The process consists on jumping between these states from 0 or for any particular initial condition. And the process consists on jumping up, like adding one individual or going down on the number of individuals. Okay, so in general, you can consider different rates depending on the level that we can call here lambda or mu. But we are interested on the particular case where the that we can model the gene expression. So what the gene expression consists on? So you start from each level is going to correspond to the number of proteins of you have inside the cell. So you can start from 0, and depending on your state, you're going to have certain rate of production, that's called Kp, or certain rate of degradation that we call mu, and this rate of degradation is proportional to the number of molecules. So it's going to be the constant times the number of molecules, mu n. So this is going to be Kp, this is going to be K as well, this also is going to be K, and so on. And from degradation, the rate of jumping is going to be from 1 to 0 is going to be 1 times 1. From 2 to 1 is mu times 2. For k to k minus 1 is going to be mu times k overall. And so on. So a particular example of this kind of processes you can see here in the plot. And you can see the stochasticity of the typical trajectory. So we are going to be interested on measure the dynamics, how the moments change over time, and what is the mean and the variance of this distribution, and compare it with theoretical observations or theoretical predictions. Sorry. So what's the idea of the algorithm? So we have now two processes. That is the difference with the previous one. The previous one only have, in the Poisson process, you only have one accumulation process. Now we have accumulation and degradation. So now you estimate, or you generate 2 times T1 and T2. That is going to depend on your particular rate. So for production rate, that is T1, you generate a random number R from 0 to 1, take the logarithm and divide by the rate, that is, in this case is K. And depending on your current amount of molecules, N, T2, that is the time to the degradation, is the same, logarithm of the random number over mu times N. If in the case that N is 0, this T2 goes to infinite. So you already know that the minimum is T1. So I want to explain you this idea later. So once we have the two numbers, the two T's, you select the minimum of them and perform the reaction that corresponds to that minimum. So let's say that the minimum is T1. So if the minimum is T1, you generate a molecule. If the minimum is T2, you degrade the molecule. And then after the degradation or the reaction, you do the same until finish the simulation. Okay, so first, after we generate the times, that T2 and T1, we check the maximum time of our reaction that we're gonna call Tmax. Okay, now Tmax is like represented by this vertical line, and in x-axis you have the time. So you're gonna have two options. The first case where the next reaction time, that let's say is this time from 0 to the first reaction. So if this time is higher than your Tmax, essentially you do nothing and let the state or the system as like it was in the beginning. In the case like that, your time to the first reaction, that is the minimum between T1 and T2, is less than Tmax, you perform the reaction. In this case, the reaction was increasing the amount. So you increase the amount of molecules and calculate again a new time. So you again select a random number. Now your T2 is going to be here with n equal to 1. Select both numbers and pick the minimum, and depending on which one is the minimum, you do the reaction. Okay, so now it seems that the minimum was production, T1. So you perform production again, and you do this until the next time to reaction is higher than Tmax. Okay, so the next time to reaction was this. And you perform that. You perform the reaction looks to be like increasing again. The next time to reaction is this. The reaction was degradation, and now your next time to reaction is this one. What happened here? It seems that the next reaction is going to occur after the Tmax. So what we do here is, given the properties of Markovian chains, we're going to discuss them later. We let the system evolve until Tmax, and we export the data and redo the same again. Okay, so I'm going to implement this algorithm now. Okay, so we start our script. Maybe I can zoom in more. So we import our libraries, pandas, tqdm, time, not I know, NumPy, and matplotlib. Okay, so we have to define the function for evolution of the system. So what things do we need for performing the simulation? First, we're gonna need the rate k, the rate mu, and the Tmax, and of course the state in the beginning of the experiment or the simulation. Sorry. Okay, we need these four inputs. So we're gonna need J, mu, Tmax, and the state. Let's call it N. We define the two times, as I explained. Logarithm of the random number and the same for T2. But in this case, this is going to be mu times n. But here we have a problem that what happens if n is 0? If n is 0, this guy is infinite. So we have to verify that this that the number of molecules is not 0. If n is positive. We select the minimum, that is going to be our time to reaction. Like the minimum of T1 and T2. And the kind of reaction is going to be which one, for knowing which kind of reaction I'm going to do, I need to know which of them is the minimum. So for knowing which of them, I use the function argmin that corresponds to the argument of the minimum. So let's see this here. For instance, let's say that this is 0.1 and this is 10. So the minimum here is the first. So we're going to have 0. If the minimum is the second, I'm going to get 1. Okay, so depending on whether this reaction is 0 or 1, I'm going to change my reaction. Otherwise, this guy is infinite, so we already know that the minimum is T1. So my time to reaction is going to be this. I think I have negative here. So I think I did a mistake in the slides, but this is negative. Yes. And my reaction is 0. Okay. So we calculate the time to reaction, and if my time to reaction is less than my maximum time, we do the reactions, or else we do nothing and only like return the state n. That is the same I got in the beginning. Okay, so in the case that this time to reaction is less than Tmax, I have to perform as many reactions as I have to do until the next time to reaction is higher than the distance from this time to Tmax. Okay, so so I'm gonna do this. So I have to define the distance from the present time or the current time to Tmax. I'm gonna call this TD, like the difference of those times. So the first TD is Tmax. Measure from 0, 0. I'm gonna take 0 as the beginning of the simulation. So I perform the first reaction. Sorry for the handwriting. First reaction, and then now my TD is gonna be TD minus the first time of reaction. That was this one. It was the first. Now my time to to my time from to Tmax is Td. Now the same, next reaction, Td is Td minus the second reaction, that is this, let's say, then minus the third, then minus the fourth, and when this Td is negative, I stop the simulation. Okay, so like more clearly, I'm gonna do it in the script. Okay. So I define Td equal to Tmax in the beginning, while Td, let's call, so I can do this, Td plus Tr, no, let's say Td is positive, or is positive here. 2. Perform this. Okay, what do we do? The reaction, no? If reaction is 0, corresponds to this T1, no? So I produce a molecule, and is equal to n plus 1. Else, n is equal to n minus 1. That corresponds to the case where T2 is smaller than T1. And I calculate a new time to reaction. That is this script here. So this guy calculates new time to reaction. And I do Td is going to be Td minus Tr. And I check if this guy is negative, I stop the simulation and return in the end n. Okay, so let's check if this makes sense. Okay, so now it ran. So we can check shortly. So let's say k is 10, mu is 1, Tmax is 0.01, and n, let's say 0. So this gives you 0. What if I make Tmax bigger? 0, 4. In this case, we have 4 reactions. 0, 1 reaction, 2 molecules, 3 molecules. Okay, so we can do this like more sequentially and check the whole trajectory. So I'm going to select a delta t relatively small, like to every time export the data. The data is going to be this array from, I'm going to start from t equal to 0 and the state equal to 0. So let's define the k. K is, let's say 10, and mu is 1. My Tmax, let's say like the total time is 10. And I'm gonna do the whole simulation from 0 to 10, but I'm gonna stop every delta t 0.01 and evolve the system during this small time and export the state of the simulation after this delta t or this dt. Okay, so k is gonna be k, that is this one. Mu is this one. Tmax in this case corresponds to the dt because I'm gonna perform the simulation for a small time interval, and n is gonna be my particular n before each round. So I will start with 0, and this function gives you n after dt. And first I evolve the system, and the time I'm gonna add the time t sorry, is t plus dt. And I save the date. So while my time is less than the total t. Okay. So I can convert this data into a data frame. Sorry. And check what the data frame looks like, how the data frame looks like. Sorry, I started here from 0, but I have to start from n. What happened here? Okay, sorry, I saved the data wrong. So this is n. This was the state from the previous script, and now I changed the name, and now it's n. Okay, now it has to be this. We can plot. Gonna be it is this one. Okay. We can run the simulation again. We get this one. And these are different samples. Yeah, so how can we check with theoretical results? How can I compare it, this plot? So usually for this kind of systems, for version that process where you have jumps from 1 or -1, I recommend you to use the Dickens formula for estimating the dynamics of the moments. So what this formula consists on? So the idea is the following. I want to check the dynamics of the moment, nth moment of n, alpha moment of n. So these brackets corresponds to the mean, or like the expected value of a given moment. So for the particular case of our simulation, the expected value of n is simply the sum of different n's for different strengths. Let's say we have 100 cells or 1,000 cells. So let's say my number of cells, scale it I from 1 to the total number of cells, let's call it capital I, and divide by I. And any particular moment, let's say the second order moment, can be the squares, the third order moment to the cube, and so on. In this case, any particular alpha. So I'm interested in how this guy, this mean or this moment change over time. So the formula tells us that we have essentially two reactions: the reaction of production, or the jump of production, and the jump of degradation. So the jump of production happens at a rate k because it's constant, and the reaction of degradation occurs at a rate mu times n. So here I want to put the reaction, and then this reaction has to be multiplied by the value of the state after the jump. So after the reaction, you have n plus 1 to the exponent. In this case, if it's mean, alpha is 1. If it's variance or second order moment is 2, minus the jump before, or the state before the jump. So before the jump, the state was n. So since the jump of this reaction is from n to n plus 1, we have the n plus 1 here and the n here. The degradation, the jump is n to n minus 1. So we put n minus 1 here. And n here because was the state before the reaction. So given this simple formula, I can get the dynamics of the first, second, and any particular moment. So if I replace alpha by 1, I have the formula for the mean. Okay, for the mean, alpha is 1. So the result of the equation is this: alpha equal to 1. So I take the expected value of the whole thing here. So this guy is a m plus 1 minus n is 1. So is the expected value of k times 1. That is simply k, because k is a deterministic function. So the expected value of a deterministic, or a constant, is a constant. And here, the expected value of mu times n times, so here you have n and n cancels out, and you have minus 1 here. So the expected value of mu times n times minus 1. And the constants can get away, or like out of the brackets, and you have minus mu expected value of n. That is what you have here. And this is the differential equation for the mean. And for the second order moment, we're going to have something similar. So observe that this guy is n squared plus 2n plus 1 minus n squared. So these two guys cancel out, and I have 2n minus 1. And the other one is essentially the same, but with negative here, with minus 2. With minus 2 is this. And finally, we have minus 2n plus 1, that times n becomes in the expected value of of this guy, no? You have here, so it's gonna be mu m times the result of this, that is minus 2n plus 1. So this is the expected value of mu minus mu n squared plus mu n. That corresponds to this second guy. So we can solve this using our more like favorite method to solve differential equations. You can use Wolfram or any other. You can solve by hand anyway, and you have this solution. The mean value of n is going to follow over time this function, and the variance, you can check that it follows also the same function. The variance is the second order moment, so we have to solve the second order moment here and rest the solution of the first order moment, I mean this squared. Yeah, and you can verify that the result is the same function. So what does this mean? Remember that in the previous session we said that the Poisson process or the Poisson process gives you the distribution of n is going to be a Poisson distribution. So for the Poisson distribution, the mean of n is equal to the variance of n. So what does this mean? Given these moments, we can claim that the distribution you're going to get is from this process is also a Poisson distribution because the variance is the same as the mean. There are other ways like to verify this, but they are too complex for the purposes of this talk. But like the main thing I want to like you to learn is like the solution for a Berthet process is also Poisson distribution with unlike the Poisson process, the mean doesn't grow linearly, but the mean follows this equation that you know probably if you have solved the charging of a capacitor in electrostatic. Okay, so we have to estimate the mean of these trajectories over time and compare it with the with this formula. Okay, so we can do this like using similar scripts for the previous session. So what we did was perform the same for 1,000 cells and save the data in a data frame and then get the mean over time. Okay, so we have this, and we perform the same simulation for n cells I in range 1,000. But now my data has to include the cell index. So we're gonna save. We're gonna start from an empty array, and I'm gonna save the first index is gonna be the cell label. T is the time, and n is the number of molecules in the process or in the cell. If I'm right, it has to run, no? Let's see what happens if it's 10. Okay, I can check. Sorry. So my columns are The first is the cell, the second is the time, and the third is the number of proteins. So you have here different cells, and if everything is fine, we have DF, okay? And we calculate from them the variance and the mean using the same script I used in the previous session. Yes, see, this is the script is in the repository. Remember that the repository link is in the description of the video. So let's call this data frame DF cells as the previous one. So for all times in the F cells, I select all the data which the time is time, and I'm gonna take the mean of the number of cells and I save it in empty, and the variance is gonna be the variance of the number of molecules, and I'm gonna save mean variance over time. You can check the data frame. So this shows you the mean and the variance over time. We can plot it. For instance, the mean. In x-axis the time, and in y-axis the mean. The mean looks like this, and the variance looks like this. Okay, so you can see here the variance is way more noisier than the mean because it's a second order moment. Maybe later in some future videos I can explain how to estimate this variability of this mean, or like the statistical estimators. So these fluctuations occurs because the number of cells I have simulated is relative low. So if I increase the number of simulations, these quantities are gonna fluctuate less. Okay, but more or less they are close to we expect. Run this again, and we can compare this to the expected means. Okay, so the expected mean by this was k over mu times 1 minus the exponential of minus mu t. So we can save, or like estimate it. Okay, let me see how this looks like before. Okay, so let's do this for 500 while I explain you what I wanted to do. Okay, so my theory is simply k over mu, these guys. Yeah, remember k over mu is going to be 10 over 1, that is 10, no? So the limit of this reaction is, or the steady state value that corresponds to the average value for t going to infinity is going to be 10 times 1 minus the exponential of minus mu times the time. The time is this. And we can plot also the time and the theory. Yeah, and you can compare them. So here is like kind of more accurate because we have more data. And if you compare the variance, remember that like the dynamic was the same as the mean. So you observe something similar, but with more fluctuation because the second order moment. Okay, we have solved now the Berthet process. We estimated the mean and the variance with from simulations. The idea here is like try to increase the population, let's say 1,000 or 10,000, and get like more detailed or more accurate moments for the simulation or the distribution. Okay, so the second thing I wanted like to show you is what happened with non-exponential statistics. Okay, so far the statistics or like the processes I have showed you have this memoryless property that corresponds like, or also Markovian processes that gives you a exponential distributed time between two reactions. It is not true that all the Markovian gives you exponential, but some non-exponential, because you can get Markovian processes with like giving you non-exponential, but let's say that we are interested in non-exponential thing. For instance, this Poisson process is non-exponential, gives you this Erlang distribution. So what happens if my process is someone such as, sorry, the statistics is not exponential between steps. One example of this is a telegraphic wave, like the example I was explaining in the previous session, where the transition time between environment is not exponential, but there has this kind of distribution. So what do we do here? So in this case, I have to track the time from the previous reaction and check if so I have to have an additional variable that is the time to reaction. So the algorithm is going to be something like this. First, I estimate the time to reaction, TR. So again, there are going to be two cases. The first case is that the time to next reaction, let's say here, the blue line corresponds to my reaction. So I start from 0, and my next time to reaction is this TR. So what happens if the maximum time is less than TR? So what do we do is similar to the previous algorithm. I let the time to evolve until Tmax, and the next time to reaction is going to be the previous TR minus Tmax. So next time I perform the next step, I have to wait this time. Okay. In the case that you can have different reactions before your Tmax, you should perform them the same until your next time to reaction is higher than the distance from the previous reaction and the Tmax. Okay, so this is the idea. I start here, and this is my Tmax. The first time to reaction was less than Tmax, so I performed the reaction. Let's say produce one molecule. So how can I get this TR? Remember that this is not exponential. This is not exponential, yes? It can be any particular distribution. So let's say gamma. So as I told you, gamma distribution is a very interesting one. Why? Because gamma is a distribution such as the random number for gamma distribution, let's say x, is always positive. So this is a very important thing because the time for us is going to be positive always. In that case, for instance, I cannot use Gaussian because or the normal distribution can give you some negative numbers. So gamma is good because it is positive. And second, you can define the gamma using two variables. The mean, let's say, instead of x, let's call it x, call it t. So for gamma, if my time is distributed, gamma is always positive, and I can define the gamma using the mean and using the variance of the distribution. But in our case, we are used to work with the CV squared. The CV squared is the coefficient of variation squared. That is sorry, I'm gonna write here. CV squared is the variance of my process over the mean of the process. I remember that the variance is the second order moment minus expected minus t squared, like the mean squared. So if we define these two guys, I can define the gamma using these two variables. I'm going to explain later how to define them properly. Okay, so sorry for getting distracted. Okay, so the first time I produce, and then I check if this time to reaction is higher than Tmax. If it's not, I perform the reaction. Then I propose the second time to reaction. I also check if the next time is higher than Tmax, in this case, or higher than this, and so on. So this, the time from the present to the next reaction is simply this T3R, TR3, minus, sorry. So I have a lot of things. Let me clear them out. It's a mess, okay. So after finishing the reactions, the next time to reaction TR is gonna be this. So what is this? This is TR1 plus TR2 plus TR3 and so on, minus Tmax. Tmax is all these guys. So this new time to reaction for the next one is going to be the sum of these three minus Tmax. I can rearrange this equation and get that. I get this as this. TR is going to be T3 minus Tmax minus TR2, T2, TR1 and TR2. Okay, so essentially what I have to do is for our Tmax, subtract every TR. Tmax minus T1, TRs minus T2. Similarly, that to the way I did in the previous example. And when this guy is higher than TR3, I stop the simulation and my new TR is this formula. Okay, so let's do it quick. So I have here, let's see how complex is this. I know it's not difficult. Okay, I have the code here. I explain you like more carefully. Okay. So first, I have a function for defining the next time to reaction. It's going to be a gamma distributed with a particular parameter called shape and another one called scale. Okay, so we can like check this guy. So this CV2 is the coefficient of variation squared of the process. So with your CV2, you can define the shape and the scale. So this particular gamma distribution has mean 1. But if you have a particular mean, you can define like your gamma multiplying the scale by the mean. Okay, so this gives you a random number with this CV squared and this mean 1. Let's say if the mean is 10, if I'm correct, this has to have mean 10. We can like verify the mean if we produce more than one random number. We can do it using size. So size is the number of random numbers I want to produce. Let's say 10. So it gives you an array of 10 numbers. If you want 1,000, you have an array of 1,000 numbers. So you have, let's say, number array. And you can, let's say 10,000. And you can plot the histogram. Yeah, I'm explaining how, like, the properties of the gamma distribution. So you have here the histogram. I can use semicolon here, like, to avoid the outputs. Change the bins. And you have something like this, and I can compare with theory. I think I have it here, if I'm not wrong. About let's do it later. We have no much time. Okay, so this is like the distribution. So you can see like the mean is 10, and the CV square has to be 1/10. Like how can we verify? We can verify calculating the variance of this guy over the mean squared. So you have something close to 1/10. Okay, so this function gives you or returns you a new time that is not exponentially distributed. So the same, if my time to reaction is, so the input of this function is the maximum time, the next time to reaction, and the state. So if the time to reaction is higher than Tmax, I return the time to reaction that is going to be Tr minus Tmax. Else, well, so I define Tt as Tmax, but this T is gonna be T max minus everything. Okay, this is that's I call TT here. And if TT is higher than TR, I stop the simulation. Okay, so if TT is, while TT is higher than TR, I subtract and I increase, for instance, the number of molecules. In this case, it's only reaction. But if you have any other particular, like more than one reaction, you select the minimum, and depending on the minimum, you perform your reaction and so on, and then you get new reactions. So this kind of approach can be helpful for us for other kind of simulations that, for instance, you have different cells, you have different reactions, and this algorithm works everywhere, always. So it's gonna be very useful in the future. And we do the simulation that is essentially the same. So I start from t equals 0, the state is gonna be 0. This is my dt. I don't need lamp. My first time to reaction comes from this function. And while t is less than t max, I evolve the system using this function, and this returns the state and the next time to reaction. So I refresh the state and the time to reaction given by this algorithm. And I save the data, the first column T and the second column S. Okay, so I can compare a single trajectory using this. So I convert the data frame, the data in data frame, and I plot the trajectory over time. You can see here. I can do this Tmax is equal to 4, so this simulation ends in 4. I can make this bigger. Same, and I can do this for many cells as we did in the birthed process. So essentially it's the same, but now I can save the data in an empty frame, and the same, the data is going to be I, that corresponds to cell, T and S. Let's skip this, guys, and just do the simulation for 100 cells. And the same. Convert the data into data frame. We have the first column is going to be cell, time and state. For cell in df.cell.unique. This, I explained this in previous session. df cell is df cell, such as df cell is equal to cell, and we can plot df cell and df state. Okay, so here I have the solution for 100 cells, the trajectories. So this looks very different to the Poisson process. It has less noise. You can also study how the mean and the see the score change over time, we can use this same script. In this case, let's call this df cells. I think it's the same, exactly. So we have, here we have state instead of n. Okay, so here is state. And we can plot the mean. We obtain this. The same for the variance. And we can increase the number of cells to check like more detailed. It seems like the variance has some jumps, like oscillations, but we have to increase the number of cells to check these oscillations. Okay, I think that's all I wanted to show you. Thank you very much, guys, for attending, and see you next time.